U1L2c set is an interesting example because it's all about a Boolean formula. And now I want to share with you this universality claim written out in this language of and not gates. So I want to prove this claim about universality. So and not are universal for Boolean circuits. Let f be a function which maps n plus 1 bits to just 1 bit. And then we may define two other functions, one called f0 and another called f1. And f0 will take in just the n bits, so x1, xn. Note that f started with x0, like I've done elsewhere up here. And this will be defined as being f with a 0 in the first place. And similarly, f1 will be defined with a 1 in the first bit. OK. So now we have two of these functions. And the way you show that you get universality with and not is really trivial. You define f of y is equal to, let me be a little more careful here. Note that I'll now define f acting on the all n plus 1 bits. So instead of just a 0 or 1, suppose I label the first bit as y. Then I have x2, x1, x2, all the way up to xn. This is the function I want to construct. And we can see that it's easily constructed as y times f0 plus y bar times f1. This is an OR gate. This is an AND gate. And I need to show you that you can get an OR gate from an AND. And I'll leave that as a little exercise because it's easy. It's De Morgan's theorem. OK, so what are the resources required to do f? By the way, you can then continue on this line and recurse. Well, if we draw out the circuit that I just used, it becomes very clear how much resource is required. So what we have is two sets of inputs, x1 through xn. There are n bits here. There's 1 bit here. This is fed into a box which computes f0, and copied and also fed into a box that computes f1. And then this bit y, a single bit here, is used to select one of the outputs of the functions, either the y0 function, the f0 function, or the f1 function. And we do that by using an AND gate, for example, and then ORing the two results together, where I connect with a NOT gate here. This is an AND. This is an OR. And then this output is F. OK, so we now see that we need to double the number of function evaluations at each stage. I will recursively simulate f0 with exactly this same pattern and just keep on going. So you can see that the amount of complexity, the resources needed, grow exponentially, at least as 2 to the number of bits used in the system. And I'll use complexity notation and say that to realize a n-bit function using AND and OR and NOT gates, you need approximately 2 to the n of such primitive gates. And so now we can get at least the universality of the AND and the NOT. In addition, we use several other resources that are physical. So I don't want this just to be a computer science argument. I want you to also think about the fact that right here we had wires that were crossing over each other. Right here we had wires that involve copying of data, something which is anathema in quantum computation. So if you're going to think about the physics of the circuit, we want to realize that there are odd resources beyond and or and not. We also had to use the resource of fan out and crossover. And of course, there are wires. So there's communication of the bits of information between all of these gates. And you want to think, if you're realizing a model of computation, how do all of those resources scale? How many crossovers, how many fan outs, how many wires do I need as I'm building something? And these kinds of questions are only recently becoming a barrier in implementations of large-scale integrated circuits as we reach limits where energy conservation, energy consumption become important to think about.